Welcome all the diploma students of mechanical engineering who are writing the DCT examination 2020. Today we are going to discuss some of the topics related to the chapter 3 of DCT syllabus, that is the thermal engineering. My name is Professor Yashwant SB, Assistant Professor, Department of Mechanical Engineering, MIT Tandavpura. Today we are going to discuss the chapter 3, that is thermal engineering of the DCET syllabus. This topic is going to cover or going to fetch you 17 marks in the DCET examination, right? Some of the topics in this chapter are the thermodynamic system and different definitions and concepts related to thermodynamic systems like open system, closed system, and different the thermodynamic properties and zeroth law of thermodynamics, first law of thermodynamics, and second law of thermodynamics. Then, in the second part, we are going to discuss the different thermodynamic processes like isobaric, isochoric, isothermal, adiabatic, polytropic process. Like this, different process we are going to discuss. Next, we are having IC engines, the working principle of two-stroke, four-stroke, petrol engine, diesel engine, and the different types or the different techniques of measuring the brake power of an IC engine, then different efficiencies. After that, we are going to discuss open cycle gas turbine and closed cycle gas turbine. Then the formation of steam and different characteristics and properties of this steam, whether it may be a dry steam, wet steam, or a superheated steam. Then the single stage and multi-stage air compressors. After that, we are going to discuss uh, refrigeration, that is vapor compression refrigeration system and vapor absorption refrigeration systems. Okay, let us start the thermal engineering. Now this diploma CET, free diploma CET coaching is carried out by the Department of Mechanical Engineering, MIT Tandavpura, in association with the Department of Mechanical Engineering, MIT Mysore. Okay, first let us discuss the definition of thermodynamics. Thermodynamics is a branch of science which deals with the heat and work and other properties of the system which are interrelated to heat and work. Nodi, this thermodynamics word consists of the two words. The one is thermi and another one is dynamics. Thermo means heat, dynamics means the power or the rate of doing work. Hence, this thermodynamics is an interrelationship between heat and work. That's why in this thermodynamics, we are going to discuss all the topics which are interrelated to heat and work directly or indirectly. Next, macroscopic and microscopic approaches. In thermodynamics, in order to study any of the substances or the characteristics of any, analyze the characteristics of any substances, we can study those characteristics in two approaches. One is microscopic approach, another one is macroscopic approach. In macroscopic approach, a certain quantity of matter is considered without the events occurring at the molecular level. We are going to treat that object or substance as a single system or a single entity, and we are going to apply our all the laws. When it comes to the microscopic approach, we are going to consider all the particles involved in that substances. The here we are going to assume that the matter is assumed to be composed of large number of molecules by considering all the events occurring at the molecular level. If you are interested to find the velocity of all the particles present in a gas, then we are going to determine the velocity in x direction, y direction, and z direction, then into number of molecules. If suppose if the gas consists of 1 mole of the substance, then say Avogadro number of molecules multiplied by the three velocities, right? That's why this microscopic approach will be very much tedious and a lengthier process. That's why in all of the thermodynamic processes, all in analysis of all the thermodynamic systems, we are going to consider the substance as the macroscopic, or we are going to apply the macroscopic approach. First, let's discuss the system. This thermodynamic system is defined as a finite quantity of matter or prescribed region of space, right? It may be any space covered by, enclosed by some boundary, or any quantity of matter right, upon which the attention is concentrated in the analysis of the problem. See this schematic diagram here. Here I consider the system as the space, two-dimensional space enclosed within this curve, and all everything present within this curve is considered as a system, and this red line is the boundary which separates the system from its surroundings, right? System, it may be any space or any object, but it must be separated from the surroundings by a definite boundary. It may be a fixed boundary or it may be a moving boundary. And a system can interact with its surroundings only in two ways. First one is ಮಾಸ್ ಇಂಟರಾಕ್ಷನ್ ಆ್ಯಂಡ್ ಸೆಕೆಂಡ್ ಒನ್ ಈಸ್ ಎನರ್ಜಿ ಇಂಟರಾಕ್ಷನ್. ಅಂದರೆ ಒಂದು ಸಿಸ್ಟಮು ಅದರ ಸರೌಂಡಿಂಗ್ಸ್ ಜೊತೆಗೆ ಎರಡು ಥರದಲ್ಲಿ ಮಾತ್ರ ಇಂಟರಾಕ್ಟ್ ಆಗ್ಬೋದು. ಒಂದು ಮಾಸ್ ಇಂಟರಾಕ್ಷನ್ ಆಗಿರುತ್ತೆ, ಮೀನ್ಸ್ ದಿ ಮಾಸ್ ಕ್ಯಾನ್ come into the system or mass can go out of the system. Second one is energy interaction. Energy may come into the system or energy is going out of the system, whatever may be the type of energy. It may be heat energy, whatever it may be, right? And system plus surroundings, if we consider both system and surroundings, then it will constitute the universe, right? Let us discuss the types of system. Based on the interactions between the system and surroundings, we are going to classify the systems into three types. First one is closed system, open system, and isolated system. In closed system, here I consider the same system, right? That is the two-dimensional space enclosed within this red curve. Now, in closed system, energy can enter the system or energy can go out of the system, but there is no mass interaction. Means this closed system is one of fixed mass, right? But energy interaction takes place. We can tell the energy interaction takes place between the system and surroundings if and only if the energy crosses the boundary of the system, right? The examples for closed system is a tea kettle, radiator of an automobile, gas confined between the piston and cylinder, etc. Second one, open system. Open system is one in which both energy interaction and mass interaction takes place. Example, if I consider human body as an open system, or if we consider human body, we are taking the food, that is the mass in. We are uh, by the excretion process, the waste is going out of the human body, mass out, energy in. If we consider if we consume the food, then the heat energy is generated within our body. There is energy in, energy out. Some amount of the heat energy is radiated from our body to the surrounding atmosphere. That is the example. Human body is an example for the open system. That is, if both mass interaction and energy interaction takes place between the system and surroundings, then we are going to call that system as an open system. Next one, isolated system. This isolated system is isolated from its surroundings, means there is no interaction, no mass interaction, no energy interaction between the system and surroundings. It is a fixed mass and energy, right? For example, perfectly insulated thermoflask universe. Next, homogeneous and heterogeneous system. First, before going for this homogeneous and heterogeneous system, let us understand the word phase, PHASE, phase. A quantity of matter homogeneous throughout its chemical composition and physical structure is called the phase. We are having the three known phases: the solid phase, liquid phase, and gaseous phase. Suppose if a system consisting of single phase, means throughout the system, if the chemical composition is same, if I consider 1 liter of water, the composition of that water H2O is uniform throughout that water bottle, and the physical structure is also same. There is the liquid. Then we are going to call such system as an homogeneous system. If the system consists of two or more phases, or if the chemical composition is different in different locations of the system, then we are going to call that as an heterogeneous system. Okay. Let us discuss thermodynamic equilibrium. This a system is said to be in a state of thermodynamic equilibrium when there is no change in any of the macroscopic property is registered if the system is isolated from its surroundings. We need to understand this sentence. If the system is isolated from its surroundings, means if the boundary is not allowing, if the boundary of the system is not allowing any type of the interaction between the system and surroundings, means there is no mass interaction, there is no energy interaction, right? Now let us forget about its surroundings. Now we are considering only the space or our system. Now, in our system, any of the macroscopic properties not changed or not going to change, then we can say our system is in a state of thermodynamic equilibrium with its surroundings. When we can say there is no change in any macroscopic property, yes, if and only if three conditions for the three other types of equilibriums are satisfied. First one is mechanical equilibrium. There is equity of forces. There is no unbalanced force within the system. That can be called as a mechanical equilibrium. If there is no change in chemical composition, that is equity of composition, that is called as chemical equilibrium. If there is no change in temperature within the system, that is equity of temperature, means if the mechanical conditions for the mechanical equilibrium, conditions for the chemical equilibrium, and the conditions for the thermal equilibrium satisfies, then we can say the system is in thermodynamic equilibrium with the surroundings. Okay, let us discuss the properties of the system. Now, if I want to describe any substance, we are going to specify that substance by some of the properties. Now, if I consider some object, we are going to specify its characteristics by means of its color, shape, size, mass, right? Likewise, here the equilibrium state of the system can be defined by certain characteristics. Those characteristics are called the thermodynamic properties or the state variables or the thermodynamic coordinates. Example: pressure, volume, temperature, density, etc. Now, if I consider 1 liter of water bottle, now it is going to have some pressure, some volume, some temperature. Now, if I describe that water present within the water bottle using any of the thermodynamic properties like pressure, volume, temperature, then such properties are called the thermodynamic properties or thermodynamic coordinates. Now, these thermodynamic properties can be categorized into two types: intensive properties and extensive properties. If any of the properties depends on the mass, right, such properties are called extensive properties. Example: mass, volume, energy, enthalpy, entropy. If any of the properties doesn't depends on the mass, then such properties are called intensive properties or intrinsic properties. Example: pressure, temperature, density, velocity, etc. Next, thermodynamic state. The condition of the system defined by its thermodynamic coordinates is called the thermodynamic state, right? Then thermodynamic state diagram, it is an XY two-dimensional XY plot where we are going to interpret the interrelationship between the dependent variable and independent variable, right? It is in like in PV diagram, TS diagram, TH diagram, etc. Then the state point, it is a point on the state diagram. For example, PV diagram, if I put any dot or if I locate any point on a state diagram, this is a PV diagram, that point corresponds to the state or the condition of the system defined by the corresponding pressure and volume. A change in state. A system is said to undergo a change in state if any of the thermodynamic properties changes. If a pressure changes from 1 bar to 2 bar, then we can say the system undergone a change of state. This change of state is nothing but the process, right? If the system changes its state from initial state to final state, then we can say the system undergone a process, right? It's the thermodynamic process. Then the path. Now the system can change its state from initial state to final state in any of the ways: by keeping the pressure constant, by keeping volume constant, by keeping temperature constant, like this. That the path followed by the system is called the thermodynamic path. Okay, then the cycle. When a system undergoes a series of processes, if I consider the IC engine, it consists of four processes: suction stroke, compression stroke, power stroke, and the exhaust stroke, right? Four processes we are having. Now, after the completion of all these four processes, our engine come back to its initial state. That is the state one, that is the initial starting of the suction stroke. Now, here we can say our system undergone a series of four processes and come back to its initial state or the original state. Then we can say our system undergone a thermodynamic cycle. Now, such process is called cyclic processes. Then non-cyclic process, if the initial state and final state are different, then we can say it is a non-cyclic process. Reversible process, if the direction of the process is reversed and if the system and surroundings can be exactly restored to its initial state, means if the direction in which the process takes place is reversed, then our system can, if the system can restore its initial state, then we can say the process is reversible. If not, irreversible process, right? This is all about the different definitions related to thermodynamics. Now let us discuss two types of walls. This wall is nothing but a separation, right? Now, if I separate, or if I yes, if I separate two systems, namely E and B or X and Y, by by means of a diathermic wall. See here, this diathermic means this wall or this separation or this membrane is going to allow only heat interaction between the two systems. ಅಂದರೆ ಎರಡು ಸಿಸ್ಟಮ್ ಮಧ್ಯೆ ಎರಡು ಸಿಸ್ಟಮನ್ನು ಡಯಾಥರ್ಮಿಕ್ ವಾಲಿಂದ ಸಪರೇಟ್ ಮಾಡಿದರೆ, then this diathermic wall will allow the heat to flow from one system to another system, but no work interaction. Then adiabatic wall is such a membrane or the separation that will allows only work interaction between the two systems, but no heat interaction. Now, with this knowledge of thermodynamic wall and sorry, diathermic wall and adiabatic wall and the concept of equilibrium, let us go for one of the famous law of thermodynamics, that is zeroth law of thermodynamics. This zeroth law of thermodynamics forms the base, the reference for the measurement of temperature. Now let us discuss the statement first. It states that if two systems are in thermal equilibrium with the third system separately. Now let us consider three systems A, B, C. If two systems are in thermal equilibrium with the third system separately, then they are in thermal equilibrium with each other. This is known as zeroth law of thermodynamics. Let us understand from this figure. Now, in figure 1, figure A, let us consider three systems A, B, and C. Here, I am going to bring system A and system B in contact with each other through the adiabatic wall. Means here A and B are separated through using an adiabatic wall. Hence, there is no heat interaction between the A and B. But B and C are separated using a diathermic wall. Means there is an heat interaction. Heat can flow from system B to system C or from system C to system B. Now, if I bring B and C in contact with each other through a diathermic wall, a spontaneous reactions takes place between the system B and C unless until if there is an thermal equilibrium with each other, there is thermal equilibrium exists between each other. Means heat can flow from B to C or C to B unless or till they are going to attain a state of thermal equilibrium. Andre equity of temperature ಬರಬೇಕು, ಅಲ್ಲಿ ತನಕ changes ಆಗುತ್ತೆ. Now they are in the same temperature, at a point of same temperature, right? Now, I'm going to bring this system C in contact with system A through a diathermic wall. Then the spontaneous reactions between A and C occurs, and these two systems A and C are going to attain a state of thermal equilibrium. Right now, if I bring A and B in contact with each other through a diathermic wall, there will be no spontaneous reactions. Means now already A and B are in thermal equilibrium. This is nothing but the zeroth law of thermodynamics, and all the explanation is provided here. Next, the concept of temperature. Temperature of the system is the property that determines whether the system is in thermal equilibrium with the other systems or is not. Now, in order to measure or in order to say the system is in thermal equilibrium with its surroundings or not, we are going to measure the temperature. This system is having so and so temperature, this system is having so and so temperature, right? By considering the temperature, we can tell that the system is in thermal equilibrium with other systems or not. Then we are having thermometer and thermometer property. This thermometer is the device or the object used to measure the temperature, and this thermodynamic property is the independent variable which can be used to read the temperature on the thermometer. Okay, these are all the different types of thermometers we are having. Constant volume gas thermometer. In constant volume gas thermometer, pressure is a thermometric property. In constant pressure gas thermometer, volume is the thermometric property. In electrical resistance thermometer, electrical resistance is the thermodynamic property. In thermocouples, thermal EMF or voltage is the thermometric property. Mercury in glass thermometers, what we are very much familiar, that is the thermometers when you came across in all the health clinics, right? There is the mercury in glass thermometer. Here the length of the mercury column is the thermometric property. Okay, this is all about the introduction to the thermodynamics and thermodynamic processes, right? Okay, now we covered almost these topics. Let's discuss remaining process. Okay, in thermodynamics, we are going to define the work as work is said to be done. See here, in mechanics, the work is said to be done if the point of application of force moves in the direction of force. But in thermodynamics, it is very much impossible to determine the point of application of force, or sometimes the system may not change its position from initial state to final state. Hence, we may conclude that this definition of work according to mechanics is quite inappropriate. Therefore, we are going to define the work in thermodynamics in a broader way. That is, if the sole effect external on the things, external things, external to the surroundings, can be reduced to the raising of a weight. I'll repeat: if the sole effect on the things external to the system can be reduced to the raising of the weight, then we can say work is done, or work interaction takes place between the system and the surroundings. Okay, different types of works. Now let us discuss the sign conventions used for the analysis of work and heat. Now, if the work is done on the system, if the surroundings is doing the work on the system, then it is conventionally taken as negative. If the work is done by the system on its surroundings, then it is conventionally taken as positive. Then similarly, for heat interactions, if the heat is added to the system, then it is taken as positive. If the heat is taken by the system or it is removed from the system, then it is taken as negative. Okay. Let's discuss different types of thermodynamic processes, right? Or the displacement work or non-flow work done in non-flow process, or the displacement work or PDV work. Let us consider a gas confined between the piston and the cylinder. Now, it is having some pressure, some volume, some temperature. Let us consider this as the initial state one. Now, if the piston moves by a small displacement ds, then the volume increases, pressure decreases, right? And it will occupy the final state 2. Now, on a thermodynamic state diagram, that is PV diagram, we can analyze this. This will point 1 will indicates or represents the initial state 1, where the pressure is P1, volume is V1. Now, if the as the piston moves upwards, what happens to volume? Increases, pressure decreases. Now, the pressure, this pressure and volume changes like this. This is the thermodynamic path and attains the final state 2. At this point, volume is V2 and pressure is P2. Now, as we all know, work done during any thermodynamic process will be given by the area under the curve. Area under the curve, right? If we want to mathematically determine that work, that is W1 to 2 is equal to integral 1 to 2 P dV, integral from 1 to 2 P dV. Now, if we make some simple substitutions, we may arrive that W1 to 2 is equal to integral P dV. Therefore, we are having different types of thermodynamic process or thermodynamic work or PDV works. First one is constant pressure process or isobaric process. It is a process in which the pressure remains the same from process during the process or from state 1 to 2. Now, in PV diagram, this process is represented by an horizontal line. Here P1 is equal to P2, but V1 is not equal to V2. Work done will be given by area under the curve. Therefore, integral 1 to 2 P into dV. Here P is constant. I am take it outside the integral symbol. Then dv, integration of 1 with respect to dv is v, between the limits 1 to 2, that is v2 minus v1. This will use the work done during the constant pressure process. Next one, constant volume process or isochoric process. In this process, volume remains the same. Now it is an vertical line. The area under the vertical line, projection of the vertical line will be a point. There will be no area. Therefore, the work done during the constant volume process is 0. Next one, constant temperature process. It is a process in which there is no change in the temperature of the system. That is isothermal process. Now, in order to determine the equation for the work done during the constant pressure process, let us consider the ideal gas equation, that is PV is equal to RT when temperature is constant, R is also constant, T is also constant, product of two constants will be another constant C, or we can modify it as P is equal to C by V. We know that PV is equal to C. If PV is equal to C, then we can apply that equation of state PV is equal to constant for both states, initial state and final state. Therefore, P1 V1 is also equal to P2 V2, that is equal to C, or V2 by V1 equals P1 by P2. Now, if I substitute this V2 by V1 is equal to P1 by P2 here, then we are going to obtain the equation to determine the work done during an isothermal process. Then that will be P1 V1 log V2 by V1, or P1 V1 log P1 by P2. Next one, polytropic process. It's a common process. The equation of state for this polytropic process is PV raised to the power of n equals constant, where n is the index of expansion or compression. The value of n varies from 0 to infinity. Now, in this equation, PV is raised to the power of n equals constant. If I put n is equal to 0, then it represents an horizontal line, that is an isobaric process. If I substitute n is equal to infinity, then it gives the vertical line, that represents constant volume process. And if I substitute n is equal to 1, then PV is equal to constant. It is an equation of state for an isothermal process. Then if I substitute n is equal to gamma, that is the ratio of specific heats, Cp by Cv, then we are going to get an adiabatic process, right? Now this is the general equation, P1 V1 minus P2 V2 divided by n minus 1. Okay, everything is written here. Okay, let us discuss another famous law of thermodynamics, that is first law of thermodynamics. We all know, we already heard this statement of first law of thermodynamics. This says that energy can neither be created nor be destroyed. The principle of conservation of energy is the first law of thermodynamics. In thermodynamics, we are going to study this first law of thermodynamics for two cases. One is for open cycle, or the non-cyclic process, or the cyclic process. First one, let's discuss the first law of thermodynamics for a closed system undergoing a cyclic process. For a cyclic process, the cyclic integral of heat is equal to cyclic integral of work. If I consider an IC engine, it consists of 4 cycles. In two process, we came across work interactions. In two process, we came across heat interactions. Now, this constitutes a cycle. In this cycle, if I add all the work quantities, that is during and adiabatic compression, we are having some work. During adiabatic expansion, we are having some work. Now, if I add these two, if I take the summation of these two work interactions, that must be equal to summation of two heat interactions. That is during constant volume heat addition, if I take Otto cycle or the petrol cycle, and there will be a constant volume heat addition, there will be some heat interaction, there will be constant volume heat rejection, heat interaction. If I take the summation of all the work quantities, that must be equal to summation of all the heat quantities. This constitutes the principle of conservation of energy, right? Similarly, we are having first law of thermodynamics for a non-cyclic process. Means if the initial state and final states are different, then the first law of thermodynamics changes its shape. Right, let's consider the system. For the system, if q will be the amount of heat added to the system and w is the amount of work done by the system on its surroundings, the net energy transfer q minus w. Suppose if I supply 50 kilojoules of heat to the system, and if it performs 20 kilojoules of heat on its surroundings, then the remaining 50 minus 20, there is 30 kilojoules of energy is going to store within the system. That stored energy is neither a heat quantity or a work quantity, and but it's also an energy that is given by the name the internal energy or energy of the system. Therefore, the difference q minus w equals delta E, where delta E is the increase in energy of the system, right? If there are one or more heat interactions and work interactions, then the first law is going to take this shape. Okay, from the first law, we are going to we uh, internal energy. The concept of internal energy came into the picture, right? Let us discuss second law of thermodynamics. The second law of thermodynamics. Why we need to go for second law of thermodynamics? Here, in first law of thermodynamics, we are having some limitations. The first law of thermodynamics states that when a closed system undergoes a cyclic process, cyclic interval of heat is equal to cyclic interval of work. Means energy can neither be created nor be destroyed. ಇದನ್ನ ಹೇಳುತ್ತೆ, right? But the first law of thermodynamics does not help to predict whether the system will or will not undergo a particular change. No idea about that from the first law. No restriction has been imposed by the first law on the possibility of conversion of energy from one form to another form. What is the possibility of conversion? What amount of energy is going to that can be converted from one form to another form? And the first law of thermodynamics does not address what portion of heat may be converted into useful energy or work. Right? These limitations of first law can be overcome by introducing another general principle called second law of thermodynamics. Before understanding the definitions of second law of thermodynamics, it's very much important to understand the term reservoir, heat reservoir or thermal energy reservoirs. These reservoirs or the hypothetical bodies, and these are the large bodies that may absorb or receive enormous amount of heat or reject enormous amount of heat without the change in temperature. ಇದನ್ನ ಏನು ಅರ್ಥ ಮಾಡ್ಕೋಬೇಕು. These thermodynamic reservoirs or thermal reservoirs are going to emit or give enormous amount of continuous heat energy or absorb enormous amount of continuous heat energy. It may give or it may receive without changing any of its temperature. Therefore, we are having two type of heat reservoirs. One is heat source or the heat or the high temperature reservoir. Second one is heat sink or low temperature reservoir. This heat source is going to absorb large amount of heat or is going to reject or provide large amount of heat energy without changing temperature. And the heat sink is going to absorb large amount of temperature, large amount of heat energy without increasing any of its temperature. and the temperature of source is considered to be high, always higher than the temperature of the sink. Now let us discuss the working principle of heat engine. As we all know, heat engine is a device which is going to receive some amount of heat energy from HDR and perform some work and rejects some amount of heat energy to its surroundings or the sink. Right? This will be an different components of an heat engine. Now we are having one famous statement of second law of thermodynamics, that is Kelvin Planck statement. This Kelvin Planck statement states that it is impossible to construct a heat engine which operates in a cycle, produces no effect other than the transfer of heat from a single thermal reservoir and performs an equivalent amount of work. What it means, for a heat engine to work, there must be two reservoirs. One is to supply the heat energy and another one is to receive the heat energy, or heat engine is going to absorb some heat energy and reject some heat energy, and it is going to perform some work. But Kelvin Planck statement states that it is impossible to construct any heat engine which receives QH amount of heat from high temperature reservoir and performs an equivalent amount of work without rejecting any amount of heat energy to its surroundings. This is highly impossible. If this happens, then efficiency will be 100%. Input is equal to output here. Input is QH and output is also equal to QH. Then efficiency is 100%. This is not possible or impossible. Next, we are having a Kelvin Planck statement. Before going for the Kelvin Planck statement, we need to understand the working principle of an refrigerator or the heat pump, or this can be called as a reverse heat engine. A reverse heat engine or the heat pump is a device which operates continuously in a cycle, removes QL amount of heat. Suppose if I consider this sink or LTR as an interior space present within the refrigerator, now our refrigerator needs to remove or extract heat energy from the interior space and rejects to these surroundings. Right here, QL will be the amount of heat energy removed from the sink and QH is the amount of heat energy rejected to the atmosphere. Now for this reverse process to take place, we need to perform some, we need to supply some external work, that is W on it. This is the working principle of heat engine, heat pump. Now, this Clausius statement states that it is impossible to construct an heat pump, a reversible engine that performs continuously in a cycle and removes QL amount of heat from LTR and rejects the same QL amount of heat to the HTR without this aid of external work. This is highly impossible. For this process to occur, we must supply some external work. This is all about Kelvin Planck statement. And the COP of, that's why the COP, that is coefficient of performance of an heat engine, will be always less than the infinity. Okay, with this discussion, we completed the concepts or the introduction to thermodynamics, different thermodynamic processes, zeroth law, first law, and second law of thermodynamics.